Hi, today redox. The redox topic is a topic that involves oxidation and reduction. Now, we need to start with knowing what oxidation and reduction actually are, but they're about whether electrons are being lost or gained. And chemistry is largely about electrons being lost or gained. And the reactions that we have is certain chemicals lose electrons, certain chemicals gain electrons, etc. And it's the fundamental part of chemistry is this looking at electrons. And redox or reduction and oxidation are just ways of dealing with that in a more precise mathematical sense. So, if you just read my heading there, basically I want you to understand that this is going to be, for your GCSE student, it's going to be a difficult topic, and therefore you're going to have to pay attention if you want to get to grips with it. So let's make a start. Well, definitions, what are they? What is oxidation and what is reduction? Well, definitions to learn. Oxidation, now you've probably come across oxidation before, like magnesium reacting with oxygen, get magnesium oxide, well, the magnesium being oxidized. Addition of oxygen is oxidation. How about removal of hydrogen? Removal of hydrogen is oxidation. The more wide-compassing definition of this is to do with electrons. Oxidation is the loss of electrons. Loss of electrons there. Now, when we've got charges like iron at 2+, as opposed to iron 3+, the value of the charge, the 2+ or the 3+, we call that oxidation number. Now, oxidation number is dealt with more precisely at A level. But if you know at GCSE that it's the charge on the ion, then if the charge increases, then that's an oxidation. Now those four ideas of oxidation are mirrored by the definitions of reduction. Reduction is the very opposite of oxidation. See, look, instead of addition, it's a removal of oxygen. Instead of removal of hydrogen, it's the addition of hydrogen. Instead of loss of electrons, it's the gain of electrons. Instead of increasing oxidation number, it's decreasing oxidation number. So they all have a different role to play in different reactions. Like when we're burning magnesium, we talk about oxygen being added. And therefore, addition of oxygen is oxidation. When we're talking about other things, we might choose to use one of these other definitions. But overall, the most important thing is electrons. Loss of electrons. Now, oil. Oxidation is the loss of electrons. Similarly, reduction then is the gain of electrons. Rig. Oil rig. I would say we're going to use oil rig idea more than anything else, and everything, whether it's to do with oxygen or hydrogen or oxidation number, it boils down to electrons being added or removed. Oil, loss of electrons. Rig, reduction is the gain of electrons. So electrons being added or gained is fundamentally what this topic is about. And when you've got electrons, when one thing is losing them, oil, then something else must be gaining them. Rig. Oil, rig. Oxidation is whatever chemical is losing the electrons, and reduction is wherever those electrons are going, because those electrons are being gained by wherever it is that they are going, and they end up there. So, in my handwritten thing at the bottom, these are different definitions. However, the loss of electrons and oxidation, the gaining of electrons, it all boils down, the topic boils down to oil rig. So learn oil rig, learn oxidation reduction in terms of electrons using oil rig, and we're going to be using that in this topic. So different types of word equations, different types of equations, whether we use words or symbols, symbol equations or balanced symbol equation. Well, in this section, we're going to introduce a new one called an ion electron equation. Now, those three, word equations, balanced symbol equations, and indeed ionic equations, where we eliminate spectator ions, those we've come across in the past. And you should be familiar with those. But now we're going to deal with ion electron equations. And those things are also called half equations. And they focus on one ion or a species. And they do not represent the whole reaction. They would only represent the loss of electrons in the case of oxidation, or they would represent the gain of electrons in case of reduction. And they're called half equations because it's like half a story. It's only half the story when we're talking about an electron being lost or gained. Half the story is in the loss, half the story is in the gain, and therefore together, when we put two half equations together, then you get the overall ionic equation. The overall ionic equation will result, which is both oxidation and reduction. And oxidation and reduction happening together is redox. This term redox, read is reduction, ox is oxidation, redox is just a posh way of saying reduction and oxidation, that they happen together. You can never ever get oxidation on its own. You can never ever get reduction on its own. The two go hand in hand. If something's losing electrons, they've got to go somewhere. If something's gaining electrons, they've got to have come from somewhere. And that's what I mean. The reduction and oxidation go hand in hand. They're called redox. And it might be hard for you to identify what's being reduced, what's being oxidized, but something somewhere is always being reduced. Something somewhere is always being oxidized. Let's look at some things you should be familiar with already. I've mentioned once or twice already the burning of magnesium. There, oxidation is the addition of oxygen. So the magnesium is having oxygen being added to it, and therefore it's forming magnesium oxide. And you might think, well, that's oxidation, isn't it? Well, it's redox. You've got to think, what's being reduced? The electrons from the magnesium go over to the oxygen, and this movement of electrons from magnesium to the oxygen cause the oxygen to make oxygen ions. And those oxygen ions are there. Those oxygen ions are what are taking in the electrons. The addition of electrons happens there. And that addition of electrons is reduction. Reduction is the gain of electrons. So the magnesium is being oxidized, yes, to magnesium oxide. The oxygen gas is being reduced to oxygen ions in that first equation. Well, what about hydrogen? Well, adding of hydrogen. The adding of hydrogen to ethene, organic topic, the hydrogenation of ethene. This is used in the manufacture of margarines, if you remember, the organic, making the alkane ethane. So, right, so I'm coming back to this one. It's a reduction. Alkenes to alkanes, why is it reduction? Well, the easy way to explain this is, well, it's the addition of hydrogen. There, addition of hydrogen. Next one, oxidation of copper metal making copper ions. Can you see? If you start with copper metal and the copper metal gives off 2 electrons making copper ions, that's going to be oxidation because the copper has lost electrons. That is a classic half equation. That can never happen on its own. The electrons have to go somewhere. When those electrons end up somewhere else, that, whatever takes those electrons in, will be being reduced. That's why I say half equations are only half the story. They're only half of a full equation. And here, it just focuses on the copper bit. The copper is being oxidized. Reduction. Now, how about gain of electrons? Well, iron 3 ions can pick up an electron and make iron 2 ions. And the gain of an electron is reduction. And again, that's only half a story. The electrons, those electrons, have got to have come from somewhere. And wherever they've come from, that has been oxidized. So that's only the reduction bit. So if we focus on just a bit, oxidation, or just a bit, reduction, focus on them together, when the oxidation and reduction are happening together, is redox, and that's a full reaction. Okay, so they're common reactions you probably have come across before today, but I want you to be able to identify them as oxidation and reduction reactions. So a bit of a mouthful, some terminology you're going to have to get used to. Whenever something causes oxidation, then we call it an oxidizing agent. If it causes oxidation, oxidizing agent. When something is an oxidizing agent, they themselves will react and they will become reduced when they themselves are behaving as oxidizing agents. So oxidizing agents cause oxidation and they themselves are reduced. Similarly, how about something that causes a reduction? Well, when it causes a reduction, it is obviously going to be a reducing agent, and reducing agents, when they work as reducing agents, are themselves oxidized. So reducing agents cause reduction and are themselves oxidized when that reaction happens. Reduction always happens together with oxidation simultaneously. Simultaneously means at the same time. The two go hand in hand together. Reactions are always redox reactions. This idea is obvious in terms of electrons. Whenever something loses electrons, it's oxidized. Whenever the reactant gains electrons, that will be reduced. And therefore you'll have oxidation and reduction together. Oil, rig ideas together. The whole thing is redox. You might have to read that a few times, but focus on the red markings and get those ideas sorted in your head. Anything losing electrons is oxidized. An oxidizing agent causes oxidation. Therefore, that will attract and gain electrons from something else. Oxidation is the loss of electrons. And so it will itself be reduced. Anything gaining electrons is reduced. A reducing agent causes a reduction. It's basically the same words again, just used in different sentences in order to give you practice at how to use the language correctly. Again, focus on the red and get to use the language in the way that it's correct and the way that it's intended. Next, we'll look at a variety of redox reactions in this topic, and we'll be counting electrons to work out what is gaining electrons and what is losing electrons. So, what do I want to talk about? There are 3 redox topics I want to talk about. The first is ionic bonding. So how do metals react with non-metals? If you remember ionic bonding, Metal joins with a non-metal. The metal loses electrons. Oxidation. The non-metal gains those same electrons. Reduction. Oxidation, reduction together is when a metal and a non-metal react together and make the compound, ionic compound. That is a redox reaction. Let's see. Right, it wasn't quite the screen I was expecting, but this is about group 1 metals reacting. Now, I can demonstrate that in a minute, but we've seen it before. I've got a 24-minute video on it from year 9 chemistry. If you want to look at it, it's there. It's in my links. You can go on to TA Chemistry and access it from there more easily, perhaps. But essentially, it's where we drop lithium, sodium, potassium into a trough of water and we see it react. Now, that's potassium. The potassium starts off as potassium and ends up as potassium ions. Now, those potassium ions are 1+. So the metal is losing electrons. The metal is being oxidized. The loss of electrons is oxidation. Oil. The potassium loses electrons, therefore it's being oxidized. If we do that with lithium and sodium, we see a pattern. We see that the lithium is least reactive, sodium is more reactive, potassium is even more reactive. The reactivity increases. Why? Well, the electron to be removed, that electron there with lithium is closer to the nucleus. That electron with sodium, the electron is further. With potassium, the electron is further. And if it's further, it's not as strongly held by the nucleus. Therefore, it can be lost more easily. If it's lost more easily, it's more reactive. That's what's going on here. The outer electron is less attracted by the nucleus, so the outer electron is more easily lost, and therefore the reactivity increases down group 1. These are oxidation reactions, metals turning into their ions. Let me show you. Let me pause it. Right, so here we have some lithium, sodium, potassium. To save time, I've taken them out. Lithium, sodium, potassium, and I did have a needle here. That needle's got some lithium on it. So very quickly, the demonstration I'm going to do will be a shortened version of the demonstration you can see for 24-minute video on from year 9. This is just tap water, and I've got a bit of lithium on the end of a needle. If I just hold it underneath, you'll see bubbles of hydrogen rising up into it, and I've put it underneath so that it's there reacting away. Reaction is a bit slow to get going because you've got oil around the outside. But when the water reacts through the oil, then we'll get quite a vigorous reaction. So lithium reacts in quite a vigorous way. Take a little bit of time for me to collect a test tube, but I can pick it up and show you there. It's reacting. That's lithium. This is sodium. Now sodium reacts in a much faster way. It's more reactive. Watch. There. The sodium has melted. The sodium is whizzing around. The sodium will move around in a melted ball until it reacts away. And it's making an alkali. In fact, they all make alkalis. They are all alkali metals. Now, how can we check that this is hydrogen? Well, we can squeaky pot test. That was hydrogen. So the gas coming off is hydrogen. And the final thing is this is potassium. Potassium burns with a lilac flame. As I say, you should be familiar with that before. So, lithium was least reactive because it's hardest to lose that electron. Sodium, that electron is more easily lost because the attraction is less attraction. It's further out. Potassium, the electron, is even more further out. The attraction is less. Therefore, that outermost electron is lost most easily. That's oxidized most easily. That's oxidized less easily because oxidation is the loss of electrons. Lithium, sodium, potassium are reacted with water, and their reactivity increases down the group. The reason reactivity increases down the group was that in all of these reactions, the metals lose their outermost electrons and they turn into positive ions. The loss of electrons I've explained. Why is potassium the most reactive? Because out of those three, it loses electrons most easily. That's why it's most reactive. Potassium atoms are bigger and the outermost electron is further, so the outermost electron's got lower attraction, and so it's lost most easily out of those three. Indeed, lithium, sodium, potassium, group 1. There is also two other elements which you can find on YouTube videos, rubidium and cesium, which react even more vigorously than potassium. The reason we don't use them in school is in that trough, we'd probably break the trough with how vigorous that reaction is with those last two. So we don't do the last two in schools, but you can see them on YouTube. And overall, the trend in group 1 is one of increasing reactivity down the group. It's increasing because oxidation is easier. The electrons are lost more easily down the group. Well, what's the opposite of that? Well, the opposite of that is reduction. And so we could talk about other things being reduced, like nonmetals. There, we're going to talk about nonmetals is the opposite of that. They react by gaining electrons, whereas metals react by losing electrons. Potassium makes potassium ions. The electrons given off by potassium, they turn water into hydroxide ions. And the hydroxide ions made is like the water is being reduced. What's being oxidized? Potassium. Potassium oxidized. What's being reduced? Water. Water gains the electrons, turns into hydroxide ions. Water being reduced, it gains electrons. So it's a redox reaction. Metals lose electrons easily. As such, metals are easily oxidized. Group 1 metals are an example. Reactive metals lose their outermost electrons. Reactive metals are oxidized easily. Some metals do not lose their outermost electrons easily, so if they don't lose their outermost electrons easily, they're not going to be easily oxidized. So there's a lot of words here. Essentially, it's all to do with whether something is gaining or losing electrons. Summarized by that phrase, oil rig. Well, now we're going to look at the opposite of that. We're going to look at group 7. Now, group 7 are nonmetals. Fluorine, chlorine, bromine, iodine, astatine. Those nonmetals all react by gaining electrons. So the gain of electrons, the small atoms, like fluorine, will be able to gain electrons more easily because the attraction will be greatest. And as a consequence, the metals at the top of the group, like fluorine, will be most reactive. Then chlorine, then bromine, then iodine. Least reactive will be astatine. Because the opposite has to happen. Here we're talking about the gain of electrons, and smaller atoms are going to be able to gain electrons more easily. The gain of electrons being most easy will make it more reactive, and the reaction will be a reduction one, not an oxidation one. So we have this practical here, where if we take fluorine, which is a yellow gas, chlorine is a green gas, bromine is a red liquid, and iodine is a grey solid. Well, fluorine is just too dangerous to use. But if I get chlorine in water, I call it chlorine water. Chlorine water. Chlorine water is pale green. I can show you these in a minute. But bromine water is pale orange. Iodine water is a brown solution. Now, if we carry out reactions between halogens and their halides, the halides are chloride, bromide, iodide. Now, if we want to use those, we use them by dissolving them in water, sodium chloride, potassium bromide, potassium iodide in water. All of them are colourless. Let me show you. So these are the halides: bromide, chloride, iodide. They are the halogen ions, ions of halogens: chloride, bromide, iodide. Now these are the halogens. Chlorine water. You can't see that so well because it's in a brown bottle. But if we pour some out, there. Now, it doesn't look, oh, there's some burnt splint there. Let me get rid of that. Right, if I pour some chlorine water out, it's pale green. Now, it might not look very pale green. It doesn't look pale green because there's not much of it. It looks colourless, but that is pale green. Bromine water is pale orange. There. Now that might look a bit yellow, but if you have enough of it, it does actually look orange. And iodine in solution is brown, a brown solution. Now, I know it might look a bit red, but if you've got more of it, it'll look brown. So they're the halogens. Chloride, the halogens are chlorine, bromine, iodine. Chlorine, bromine, iodine, they are the halogens. And the ions of those, the ions are chloride, bromide, and iodide. And we have a famous practical where we put these halide ions with the halogens, and we see what reacts with what. Now, to save me doing that, I've got the results on this table. And it's practical. And these results allow us to work out the order of reactivity, which you should be able to predict anyway. But the order of reactivity is found by mixing together the ions, the colourless solution of chloride, bromide, iodide, mixing them with pale green, pale orange, brown solutions, and seeing where we get a reaction and where we don't get a reaction. So we get a reaction at there, and there. We get a reaction at reaction 2, 3, and 6, and we don't get a reaction at 1, 5, and 9, and we don't get a reaction at 4, 7, and 8. And then we have to be able to explain that. And the explanation will lead to knowing which halogen is more reactive. So, where we get reaction, stuff like that. Chlorine will react with potassium iodide. And chlorine will react with iodide ions, because they're the halide ions, making chloride ions and iodine. And the more reactive halogen ends up as the ions. So this shows you that chloride ends up as ions and therefore is more reactive. You see a reaction there. Well, what about 3 where there's no reaction? The 3 where there's no reaction, 4, 7, and 8, are where the halogen here with the halide, well, the halide is more reactive. It shows you that chlorine is more reactive than bromine because you get no reaction. The chlorine is already as chloride ions and therefore being more reactive, it will stay. And where you get no visible reaction, that's like where you're reacting the same halogen with its ions, you may or may not be getting a reaction. But whether you get a reaction or not does not matter, because as a consequence of the reaction, even if there were one, you would make exactly the same things as you had to begin with. So there's no visible reaction. You could have an intellectual debate about whether there's a reaction going on at all. And I would say yes, there's a reaction going on, but the reaction does not make anything new. So we don't see anything happening. And the result of all of that is, well, you can work out which is more reactive. Chlorine more reactive than iodine. Chlorine more reactive than bromine. Equally, we can work out bromine is more reactive than iodine. And therefore, the reactivity as you go down the group gets less and less and less reactive. Having established the reactivity of the elements gets less down the group, then we can say the reactivity of the elements increases up the group. Why? Well, it's all to do with gaining an electron. Which of the halogens will gain electrons most easily? Halogens are reduced. That's the gaining of electrons. So they need to gain electrons. The atoms that are smaller as we move up the group. So the chlorine atoms are smaller than bromine atoms, are smaller than iodine atoms. The smaller atoms can attract outside electrons most strongly than bigger atoms. So the gain of electrons happens most easily with smaller atoms, and the reactivity increases as you go up the group. As you go towards smaller atoms, the reactivity will be more and more and more and more. And that's in contrast to metals. Metals increase reactivity down the group. Non-metals increase reactivity up the group. Because metals are losing electrons when they're reacting. Non-metals are gaining electrons when they're reacting. So, the smaller atoms of metals find it harder to lose electrons. The smaller atoms of non-metals find it easier to gain electrons. And that's why you see this difference between groups that are metal, like groups 1 and 2, their reactivities get more and more as you go down the group because they lose electrons more and more easily. Whereas groups 6 and 7, their reactivity increases as you go up the group. The ones at the top are most reactive, and as you go down the group, they get less and less and less reactive because they're doing the opposite. They're gaining the electrons. So here we've got sizes of atoms and molecules. As you go down the group, the atoms are getting bigger and bigger and bigger, and as they get bigger and bigger and bigger, they're not going to be able to attract electrons as strongly. Non-metals react by gaining electrons. These are halogens when it's the molecules, and the ions of the molecules are called halide. Halide ions are these things, and halogens are those things. Fluorine is the most reactive non-metal. As its molecules are made up of the smallest atoms, they attract electrons most strongly, and therefore they lead to fierce reactions. Hopefully by now you appreciate the metals lose electrons easily and the non-metals gain electrons easily. So metals that react with non-metals, that's a redox reaction. Right, let me see if I can quickly show you something. Actually, I don't think I can because I've not got a deflagrating spoon. I can try and tell you what I would have done, and it's probably not worth doing again in another video, but I've got an empty gas jar here. I was going to put chlorine gas in there, and then get some hot sodium in I need a deflagrating spoon, and plunge the hot sodium into chlorine. Chlorine and sodium make sodium chloride. Chlorine and sodium are elements. Sodium chloride is the compound. I was going to make the compound for you, but without a deflagrating spoon, I'm sorry, I can't show you that. I might show you that in a future video or at A-level. When I do my A-level videos, I'll put that in. But now I'm going to ask you to use your imagination. That's novel, isn't it? Imagination. Look, sodium. Sodium, you've come across it before. Sodium, solid, heat it up, chlorine, non-metal, green gas. The two react together and make sodium chloride. You know it's ionic because it's a metal reacting with a non-metal. The metal loses electrons. The non-metal gains the electrons. The metal turns into sodium ions, that's oxidation, and the electrons go from the metal over to the non-metal, and they turn the chlorine molecules into two chloride ions. Now, that's all a bit difficult to think about, but if you separate that full equation into two half equations, you'll see the oxidation and you'll see the reduction displayed in these half equations, ion-electron equations, in a very elegant way. Look, sodium turns into ions and two electrons are given out. Those two electrons there are the same electrons that react with chlorine molecules, turning them into chloride ions. So that's the overall equation, balanced symbol equation. That's a half equation or an ion-electron equation to show oxidation. This is an ion-electron equation to show reduction. And overall, if you add these two, like you see, two sodium, chlorine gas molecules there. That's on the left. These are on the right. Sodium ions, two chloride ions, and the electrons on the left and the electrons on the right would cancel out if you bring them together and write the overall equation. Metals reacting with non-metals. Now that making sodium chloride is just one example, but that will happen whenever you get ionic bonding. Ionic bonding, the metal will lose electrons, oil. The non-metal will gain the electrons, rig. The two half equations can be written. One is for oxidation, that's the metal, and the other is for reduction, that's the non-metal. Combining the two half equations by balancing them all up will give the overall ionic equation, or the overall balance symbol equation. If there's nothing else involved, you can get it that way. Right, so that's the end of that. That's part one to my 3-part redox series. And really, it just focused on metals losing electrons, non-metals gaining electrons, fundamental ideas which we use over and over again at A-level, and we introduce them here and now. And from now on, those ideas, I hope you understand, really important ideas, you understand them to help you with your future chemistry. All right, lads, see you next time.